Adrienne did her PhD at Caltech. She was in Uchibachi, preceding me. And she went on to CETA and Perimeter Institute, where she had a CFAR fellowship in gravitational physics and cosmology. And she's been assistant professor at UNC since 2013. She just got a career award last year. She works on the general questions that her work addresses are: what are the initial conditions of the universe, and what is dark matter? This is going to be an example of this, but I should say that Adrienne has also worked on, for example, modified gravity. The most cited paper is on testing FOVAR gravity with the solar system. But today we're going to hear about this module.
Turn off the light.
You turn the lights
Oh, the light, yeah.
down a little bit.
Good?
I think that's probably good.
Yeah.
Yes? Is that good?
All right.
I'm a theorist. I don't have that many pretty pictures of galaxies. I'm sorry to disappoint you. So it's a pleasure to be here this afternoon. This is actually my first time visiting NYU. And I'm going to tell you about how we can use something that we know absolutely nothing about, dark matter, to learn about something that we know absolutely nothing about, which is the evolution of the universe during its first second. Whenever we talk about cosmology, we've got to actually just start back to the idea that the universe is expanding. So to get on the same page of reference, and what do we mean when we talk about an expanding universe? What we mean is a universe that's well described locally by Hubble's law, that we have a apparent recessional velocity that's proportional to the distance away from us with some constant proportionality, the Hubble constant. The picture that we have of this expansion is, imagine that you have a grid throughout the universe, a three-dimensional grid filling the universe. And galaxies live at fixed locations on this grid. And then the grid itself is expanding with time. So if I start out 11.6 billion years ago, all these galaxies are pretty close together. They keep the same location on the grid, but the actual spacing of the grid lines is increasing. This is what I mean when I say it's important to remember that the expansion of the universe is not an explosion in space. It's not that the stuff in the universe was all at one spot and then exploded out and started traveling through the void. It's an expansion of space. It's the actual creation of new space between galaxies. So if you take nothing else away from this talk, I'd like you to take that away. That what we're talking about here is that we have the creation of new space between galaxies. Namely, another thing I want to point out here is my grid here is only limited by the size of my slide. It has no edge. So there's a galaxy here, there's a galaxy here, there's a galaxy here, there's also a galaxy over there, and over there, and over there, and over there. The grid is endless. And then as I go back in time, it's just the grid spacings are changing, but the grid is still endless. When we talk about the Big Bang, what we mean is that instant when the grid lines were all infinitely close together. But there were still infinitely many of them. It wasn't like there was an empty part of the grid that had not yet been reached. So the clock, the way we describe this is we describe everything in the universe as having some distance from us that is the product of a scale factor, A of t, that describes how the spacing of the grid lines, and then its co-moving distance, which is basically how many grid cells it is away from us. The co-moving distance does not change in time. The scale factor does. And so on here, the way I've drawn it, this would correspond to A over A today of 0.75. This is A over A today of 0.5, A over A today of 0.25, and A over A today being 0 is what we mean by the Big Bang. So in a lot of the rest of the talk, I'm actually going to be using A, this scale factor, as my clock. It's a much better clock when we're talking about the history of the universe than time is. It's a measurement for how big the universe has grown. So as the universe expands, the content within it evolves. This is a sketch of the log of the energy density as a log A, which I'll remind you is kind of, think of it as the size of the universe. So today we live in a universe that is 70% dark energy. We don't know what that is, but we know that its energy density is roughly constant as the universe expands. 30% matter. Matter, if you have rocks in a box and you expand your box, the density of rocks in your box goes down by 1 over volume. So matter, as the universe expands, the density in matter goes as 1 over a cubed, 1 over volume. And then today we have a trace amount of relativistic particles, radiation. However, if I look back in the early universe, not only does, as the universe expands, the number density of photons goes down as 1 over volume, but the energy in each photon goes down as 1 over a, because the actual wavelength of the photon gets stretched as the universe expands. So this means that the density in radiation goes as a to the minus 4. So if I go back in time, in the early universe, 1 second after the Big Bang, the universe was basically 100% radiation. It's a radiation-dominated universe. This is the fireball universe. Remember, it's an endless fireball. There's no edge to the fireball. The whole universe, infinite in scope, was all one big fireball, with temperature of 10 billion Kelvin, or in units that I prefer, 0.85 MeV, and that is at the 1 second mark. So it's interesting when the universe is this hot. You can do some interesting things in a universe that is this hot. This temperature is comparable to the temperature inside the sun. So the entire universe, 2 to 3 minutes after the Big Bang, underwent a process of Big Bang nucleosynthesis. So the entire universe was hot enough that protons and neutrons could hit each other with sufficient speed to fuse and form helium nuclei. This led to about 24% of all of the atomic matter in the universe being bound into helium. This is far more helium than all the stars that have ever lived could possibly make. And we measure it. We measure the amount of helium in our universe, and we find that it precisely matches the predictions of Big Bang nucleosynthesis. And so cosmologists everywhere take a big victory lap, and we feel very proud of ourselves. And so the one thing we know about the early universe was that the 2 to 3 minutes after the Big Bang, it was hot and helium was created. Nothing much happened then for the next 380,000 years. The universe kept expanding. The universe kept cooling. The radiation bath eventually dipped below in density to the matter bath. And 380,000 years later, the temperature of the universe now has fallen to just a relatively balmy 3,000 degrees Kelvin. And now it is possible for the electrons to be captured by the helium and hydrogen nuclei and form atoms for the very first time. Any atoms that would try to form before this would be quickly destroyed by a hot photon that was flying through the universe. But now the ambient temperature of the universe is cool enough that these atoms can form and they can persist. Yassine is an expert on this process. This was an incredibly important transition in the early universe because before this, the universe was filled with this hot plasma of ionized hydrogen and helium. After this, the universe is filled with atomic hydrogen and atomic helium. Atomic hydrogen and helium is transparent. So this is when the universe became transparent for the very first time. If we then consider the life history of a photon, so here it's far, far away from us in the distant past, we have a bunch of photons and the primordial plasma of protons and electrons and helium nuclei. And the photons are bouncing off these charged particles. They can't go very far before they hit a charged particle and bounce off. Then the universe cools to the point that hydrogen forms. The universe becomes transparent. And those photons start traveling uninterrupted in a straight line. And they travel in a straight line for the next 13.8 billion years until they reach our detectors on Earth and in orbit. And we see them as a uniform glow across the sky. This is the cosmic microwave background. It provides us a picture of what the universe looked like the last time these photons interacted with anything, back when hydrogen was formed 380,000 years after the Big Bang. Is there a question?
I have a silly question. So what was the major radiation matter interaction? Was it Compton scattering?
So yeah, it's Compton scattering. Thompson scattering.
Compton scattering. Thank you.
Photons out the electrons. So this is what it looks like. This is the cosmic microwave background, as seen by the Planck satellite. The galaxy has been removed from this. This has been cleaned. And what you're looking at here is basically a uniform black body spectrum with a temperature of 2.7 degrees Kelvin. But different points have slightly different microkelvin fluctuations. So the red points here are tens of microkelvin hotter, and the blue points are tens of microkelvin colder. These are very tiny temperature fluctuations. And this is a picture of what the universe looked like 380,000 years after the Big Bang. This tells us a lot. We can then take these initial cold spots and hot spots. These indicate regions of the universe that were initially a little more dense and a little less dense than average. So all these cold spots here actually correspond to places that have a little more matter than average. The hot spots correspond to places that have a little less matter than average. The reason for the kind of inversion in that temperature is it's actually the gravitational redshift that dominates. We can then put these type of fluctuations of hot spots and cold spots, overdense and underdense regions, we can put those into a computer and simulate what would happen next. The answer of what happens next is that gravity gets into the action. And gravity is the universe's construction agent. Gravity will take a region of the universe that has just a little bit more matter than average, and will pull more matter towards it. Now that region has even more matter than average, so gravity will pull even more matter in. What happens is if we start with something, this is a simulation, where you have put a uniform distribution of particles, so these particles are matter particles, and they're pretty uniformly distributed when the universe is 280 million years old at the start of the simulation. So this distribution is inferred directly from the cosmic microwave background. Then gravity starts working, and you can see gravity starts clumping the matter into a higher density region and opening up these voids where there is no matter. You go a little further, and you see these magnificent voids and filaments, this kind of cosmic web structure. And you go further to today, and you see you have very high density regions separated by filaments and voids. And when you compare these simulations to a map of the distribution of galaxies that we see, it looks pretty good. When we plot galaxies, so each point here is a galaxy in space, we see the exact same kind of voids and filamentary structures, the so-called cosmic web. We feel very proud of ourselves. We've got this. We understand the entire evolution of the universe. Of course, what goes on inside galaxies is complicated, but I'm a cosmologist, so as far as I'm concerned, they're point masses. Zooming in on what this process looks like. So this is, I'm going to show you a simulation. I picked this simulation because it's actually one of the few simulations I know of that shows it nicely in physical units. So what you're going to see here, these are all particles. You're initially going to see them all flying out. That's the expansion of the universe. So initially everything's flying away from everything else because they're all just stuck on the co-moving grid, and the co-moving grid is expanding. But eventually you're going to see that gravity turns things around and starts an infall, a collapse. So initially everything's expanding out, but if you look at the center, you can start to see that some particles are starting to fall back in. They're turning away from the expansion and falling back in. You can see that a steady spheroid of matter is forming in the center that is no longer expanding. So stuff on the outskirts here is still going out, but this area here is now reaching kind of a steady state. Yes?
What do you mean by the center?
So this was the original center of the overdense region. So this was set up to have an overdense region in the center. And so the idea here is that we live in a galaxy like this that's surrounded by a dark matter halo around it. And I'll talk in a minute what exactly dark matter is and isn't. But it's matter. It's gravitationally bound. And so this would be a picture of something that would like be our home. We would live right here in the center. We're surrounded by this clump of dark matter, and a galactic halo like this has many, many smaller halos, clumps of dark matter inside it. So this is the picture that we are left with. Yes?
I'm just curious, what's the color of this cartoon? Is that number
This?
density? No,
The color indicates density.
Oh,
So bright just means high density.
okay. The density of stars?
Density of particles. Right now they're just little particles.
Okay.
Let's remain agnostic for the moment about what these particles are, but they're just particles.
And particles interact by gravity only.
Particles that interact by gravity only, yes. So, if we knew where the fluctuations in the cosmic microwave background came from, we'd be golden. That's my message here. That if we can start with knowing where the fluctuations in the cosmic microwave background came from, then gravity can take it from there and build us our universe with galaxies and structures and filaments and web and everything. So then we have to ask, okay, where did these fluctuations in the cosmic microwave background come from? So this is a way we plot them. This is the average temperature fluctuation as plotted as a function of the separation between the 2 points. So what you can imagine doing is to get this plot on this graph, you go out and you measure the relative temperature difference between all points on the sky separated by 2 degrees. You square it and you take the average. And you get this oscillatory feature. There are only a few features of this that are going to be relevant for us. This scale with the big peak in characteristic fluctuation size at about a degree corresponds to the cosmological horizon at last scatter, i.e. how far a photon could have traveled at that time. Everything smaller than that is plasma physics, which I'm not going to talk about. Part of this that really interests us is over here on large scales, because these are the fluctuations that were there initially. These are the fluctuations that gravity has not had any chance to affect yet. These are fluctuations that are there as kind of the initial condition. And if we can extrapolate and basically run the movie backward, what does the initial condition need to look like to get this nice oscillatory figure? It looks like this. Basically the same fluctuation amplitude on all different wavelengths. This is the scale invariant power spectrum. So you need to have the same amplitude of fluctuation on all different wavelengths. And if you can start with that, then you match all the observations of the CMB.
How do you see that it's the fluctuation is the same on all scales?
So basically, if you take this as your initial condition and you run the plasma physics forward, you get this.
Okay.
So this leaves us with more questions. Where did these fluctuations come from? Why are they the same for all separations? And why aren't there more extreme fluctuations? Why are we only talking about microkelvin fluctuations? Why aren't there, order unity fluctuations? And the answer to all these questions led to the proposal of a very radical idea of inflation, a period of accelerated expansion in the early universe. So the content of the universe determines how the universe expands. This is what general relativity tells us. So a universe that's filled with radiation or a universe that's filled with matter, they both decelerate. The expansion slows down with time. Gravity is trying to pull everything back together. Inflation is the opposite. Inflation is a moment of accelerated expansion. A little growth spurt, if you will. So these are some times on this plot, where the universe's volume doubled at least 260 times, basically instantly. Equivalently to the universe going from the size of a proton to the size of an astronomical unit. Basically instantaneously. An exponential expansion. So in a plot of radius of our observable universe versus time, inflation is this instant rise. During inflation, the Hubble rate is exponential, or very close to it. What can do this? Not matter, not radiation. Basically, the idea is it was a scalar field. And why a scalar field can do this is its energy density, in the right conditions, is not diluted by expansion. So this is a source of energy that as the universe expands, its energy density does not change. That can give you this exponential expansion. And then inflation ends when this scalar field decays into radiation and you resume your regularly scheduled hot Big Bang with the formation of helium and the formation of the cosmic microwave background all the way to today.
So essentially, the scalar field is similar to dark energy, which is also invariant.
Yes. So there have been many, many efforts to try to unify these things. Because you're absolutely right. The dark energy has a lot of the same properties as the inflaton. The problem is the absolute values of those energy densities are radically different. So if I put the inflaton density on that very first plot, it would be many, 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 many orders of magnitude above the constant energy density we see as dark energy today.
So it's much better at expanding the universe.
So it expands it faster, yes. So why do we do this? Because inflation gives us an initial origin story for our fluctuations. Quantum mechanics tells us that it's impossible for the universe to be exactly uniform everywhere. There are always going to be little energy fluctuations, a little bit more energy popping into existence here, borrowing a little energy from over there. These fluctuations are always happening underneath the surface. It's just in a normal, decelerating universe, they just kind of pop in and out of existence without causing us much trouble. But if the universe is accelerating, then it's possible for these fluctuations to basically pop into existence and then be stretched out to the point that then they can't pop out of existence. It's kind of analogous to Hawking radiation. What this does is it freezes these quantum fluctuations in place, and it lays down a spectrum of fluctuations. So you can imagine that at some early time I have this little fluctuation, the quantum mechanics sets its amplitude, it gets stretched, and a new fluctuation gets laid down on top of it. That fluctuation also gets stretched, and a new fluctuation gets laid down on top of that. The same quantum mechanical principle acting each time. And then we see a sum of all these fluctuations, which is a sum of fluctuations with the same amplitude on all different wavelengths, which is exactly the feature we needed to explain the cosmic microwave background. So inflation produces nearly the same fluctuations on all wavelengths. So, why aren't we done? What is left for cosmology to do? We've got some questions about inflation. What caused it? What was the scalar field? We call it the inflaton. And what was the inflaton? It's the field that drove inflation. How and why did inflation end? I don't know. Because I don't know why it started, so I don't really know why it ended. We also have some questions about the universe's content. I've been kind of glossing over here. I've just been saying, matter. Only 4% of the universe is baryonic matter. Protons, electrons, atoms. Yes, I know electrons aren't baryons, but they are to cosmologists. 26% of the universe is something else. It's matter. It acts gravitationally like matter, but it has to be a stable, neutral, at temperatures of 3,000 Kelvin and above particle. And no known particle fits that description. So this is some new particle. That's the dark matter. And then we have this dark energy. So we have the mysteries I'm going to focus on for the rest of the talk is kind of what is this dark matter and where did it come from? And what about inflation? What caused it? How did it end? And a part of the story is inflation leaves an empty universe. Whatever was there before inflation gets completely diluted by inflation. So where did everything else come from? How did the universe fill up again after inflation? So what we have here is a gap in our cosmological timeline. This is the history of the universe as seen by a cosmologist. So we live here when the temperature of the universe is a cold 10 to the minus 4 eV. The cosmic microwave background was created here. Big Bang nucleosynthesis happened here. And then inflation happened earlier. And then we have a gap, a hole in the record. We don't know much about the later stages of inflation. And we don't know how we got from inflation to radiation domination. And so in the second half of my talk, I'm going to talk about some ideas that we're having of how to get at answering these questions. How do we fill this gap? So the second part will be on probing inflation with mini-halos. And the third part will be probing this gap with microhalos. So probing inflation with mini-halos. This is work that was primarily done by my graduate student, Sten Delas. Very, very impressive young man who will be graduating next year. So how do we actually understand inflation? How do we probe inflation? We probe inflation using these perturbations. So I had this cartoon before, this idea that you have wavelengths being laid down one on top of another. And then what we observe is the cosmic microwave background, which we can separate by a Fourier transform into perturbations at different wavelengths. And so those perturbations at different wavelengths are effectively a historical record of what happened during inflation, with the smaller wavelengths, like the yellow here, probing the later times of inflation. So the amplitude of these different wavelength perturbations tells you what was going on during inflation when those wavelengths were created. And we plot this in terms of a power spectrum. So this is basically giving you the average amplitude of a fluctuation, the average amplitude squared, of a fluctuation with this wavelength. And we know this power spectrum really, really well at large scales, courtesy of the cosmic microwave background. That's right here. But on small scales, all we have are upper limits. We really don't know anything except that it's below order unity. So everything that's shaded here is allowed. And what's commonly assumed is just take what we see on large scales and extrapolate it down to small scales. But there's a lot of interesting inflationary physics that would predict something else. Interactions during inflation can give you a spike. Different stages of inflation could give you kind of a plateau feature. Different models of how inflation ended would lead to a runaway power spectrum or a sharp waterfall type power spectrum. All of these would tell us a lot about how inflation happened and how it ended. And yet we don't have good probes of any of this. One probe we could hope to have would be the dark matter. So if a region of the universe initially has an overdensity that's just 0.1% more than average, then at very early times, about the time of the cosmic microwave background, the dark matter in that region will collapse to form a halo. And these are called ultra-compact mini-halos. They're early forming halos that come from extreme overdensities in the initial conditions. And we could go out and look for these. And that would tell us something about inflation. And so what we do is the probability of forming an ultra-compact mini-halo depends on the probability distribution of the density fluctuation. So this is the fractional density fluctuation. This is the probability of having that fluctuation. And so you can see that this would be the threshold for forming an ultra-compact mini-halo. If we live in the red universe with this probability distribution, you wouldn't form any at all. Whereas if we lived in the black universe, you'd form a lot. And so we can relate constraints on the number of ultra-compact mini-halos directly to that power spectrum of inflationary perturbations and try to learn something about inflation. And in fact, that is exactly where this red region comes from. If you use this technique, looking for dark matter in these ultra-compact mini-halos, you can rule out this red region. Assuming the standard assumption that ultra-compact mini-halos are very rare and formed by radial collapse, and therefore have a density profile that's given by radial infall theory for exactly perfect spherical radial collapse. So we wanted to test this. So what we did is we modified a simulation code to include a smooth radiation component. This plot just shows that we're matching the linear theory prediction in our simulation. We put in a spike in the primordial power spectrum, and then we made an ultra-compact mini-halo inside of our simulation. Here it is, the ultra-compact mini-halo forming. Again, density here is being indicated by color. So the brighter the color, the more dense dark matter is in this region. And you can see that indeed, right at a redshift of 1,000, we went from just being an over-dense blob to being a nice halo, a bound object. This is our initial condition with this extreme region that we selected for. Indeed, that extreme region forms a halo long before any other halos form. So this halo was the first of its kind. But it didn't stay lonely for long. You go a little later in the simulation and there's lots and lots and lots of halos. So what's its density profile? The inset here shows the density profile, density as a function of radius. And you can see it is shallower in the inner region than rho going as minus to the 9/4. How much shallower, shown in the big plot. I'm plotting here rho times r to the 3/2. And you can see that it basically plateaus. The different colors here are different redshifts. So you can see as time progresses, the halo is growing as the background density falls, but the inner region is very steady. It's not evolving. And it has a density profile that's given by a modified Moore profile with the inner slope of 1.5. And this is very stable with time, unless there's a merger. So one of our halos did experience a merger, and its halo got a little bit disrupted as a result. So what does this mean for using ultra-compact mini-halos to probe the primordial power spectrum? So what we found is that microhalos that form from spikes in the primordial power spectrum have density profiles with r to the minus 3/2 in the inner region. We also simulated plateaus, and we found that they had the standard NFW profiles that you see in normal simulations. Together, this would reduce the dark matter annihilation rate, the probability of one dark matter particle finding another dark matter particle and annihilating into something that we can see, which is how we search for these things, by factors of hundreds, which reduces our ability to constrain the abundance of these objects through gamma ray observations by thousands. So the signal from each individual halo just got a lot weaker. So this is the bad news, that this was a faulty assumption that these halos would have the steep profile given by radial infall. They in fact have much shallower profiles, and this makes them much, much harder to detect. Yes?
So in that plot that you showed, the deviation from r to the minus 9/4 was apparent only like pretty deep inside, but that's where basically all the annihilation was happening.
That's where all the annihilation is happening. So that inner region dominates the signal.
Just to get a sense, I mean, what kind of feature output is requiring the inflationary potential? Is this something dramatic or?
So this would be a feature you can kind of judge from the exclusion plots I showed that would amplify the power spectrum by about 3 or 4 orders of magnitude beyond the base extrapolation, which you can get from like particle production during inflation or some kind of bend in the inflationary trajectory.
You have to assume cross-section from a dark matter annihilation. So
Yes.
that must be another thing that you can turn where, I don't know, it
Not-
sort of influences your results, I guess.
Somewhat, but what the assumption that goes into this is that the universe, that dark matter was created in a radiation-dominated universe, and if you make that assumption, that it was created thermally in a radiation-dominated universe, then you know the cross-section. And I'll get more into details about that in a minute. But yeah, the assumption for the cross-section here is that it was thermally produced in a radiation-dominated universe, and then you do know the cross-section. So this was, like I said, bad news. But up until now, all prior efforts to use microhalos to constrain the primordial fluctuations have only considered these freakish, early-forming microhalos. They totally neglected all the other microhalos that would form. We have all these microhalos. Why not use them? And so we did. We developed a model that allowed us to predict the density profile for all of these halos based on their formation time, and then used the statistics of the power spectrum to predict how many halos would form as a function of formation time, and compute an annihilation signature from that. And what we find, so this is constraining a delta function spike in the power spectrum. This is a toy model. So imagine putting just a delta function spike. The amplitude here is shaded is ruled out by Fermi-Lat observations of dwarf spheroidals. Oh, not dwarf spheroidals, that's the next section. These are the fact that Fermi hasn't seen any point sources consistent with these halos. The solid line here is what you would predict for the upper bound on the amplitude of this spike using the old ultra-compact mini-halo picture with the steep profiles but only considering the first forming ones. This is what we get with our method of having the shallower density profiles but considering all the halos. And it's actually a more powerful constraint. Same goes for the diffuse bounds. So our power spectrum bounds are actually more powerful because even though each of our halos are weaker, we're using all of them instead of just the early forming ones. So to conclude this part, the takeaway message I want to say is that yes, these ultra-compact mini-halos are not as bright and easy to find as we thought they were. But you can still use mini-halos to probe inflation. They are still an extremely powerful, by far the most powerful probe that we have currently for probing inflation on these scales. You just have to use the entire ensemble, not just the first generation halos. And then you can get even better constraints. Now improvements are underway. We're working on this still. We're improving our model for the density profiles. We need to still include the effects of mini-halo mergers. What it looks like is that mergers will soften the profile back down to an NFW profile, a shallower profile. And so we showed how that weakens the constraints here. We also have to take into account that mergers are going to destroy some of our halos. So if half of them are destroyed, that weakens the constraint to the red line. We want to look beyond a delta function, and eventually relate this directly to inflation. And so this is very much a research program that is still in progress, but it's showing a lot of promise.
What exactly do you mean by the old constraints only considered the early forming halos? What does that mean exactly?
So they were only considering kind of the freak halos that formed super early in total isolation.
How did they even isolate those in their prediction?
So they were basically constraining like a 6 sigma fluctuation in the density field. Very, very rare fluctuations, extreme rare fluctuations.
Yeah, okay.
So your constraints are more sensitive at some co-moving wave numbers than others. So what sets the 10 inverse megaparsec?
So this basically is, so the wavelength that's sensitive to is the mass of the halos. So if you go too small in halo mass, so smaller goes this way.
Yeah.
So as you go smaller, the signal from each halo is weaker. So the point source bound becomes weaker because you can't see them as bright. As they get bigger, the signal is stronger, but you have fewer of them. And so it's a competition between those effects. And so the sweet spot turns out to be about a solar mass. So that's using mini-halos to probe inflation. The next idea I wanted to talk about was using mini-halos, and now I'm actually going to switch to calling them microhalos, and I will explain why in a second, to probe this gap. So this is by no means a standard distinction, but I'm trying to make it so. When I say mini-halo, think solar mass or 10 solar mass. The stuff I was talking before, we're basically looking at solar mass, 100 solar mass. That's where the sweet spot was about 10 solar masses. When I say microhalo, think Earth mass. Smaller. We're going smaller now. And we're trying now not to get at inflation, but rather to get at the gap between inflation and Big Bang nucleosynthesis. So that gap is only a second long. But let me put it a different way.
Adrienne, I'm embarrassed. Maybe you said and it just slipped. Going back to the other, you can't use the power spectrum in that range, I guess, to constrain it. Are you assuming something about the annihilation cross-section? Or is it like some Poisson fluctuation? How do you just said that you could constrain.
Right, so I'm assuming a standard cross-section based on being a thermal relic. So I'm assuming a cross-section.
So you could just as well say you exclude that model because if dark matter doesn't have any particles, there would be no signal.
Right. Then you can't use microhalos. You have to look for gravitational effects from the microhalos to try to probe inflation this way. And that has been done. That hasn't been done with the new density profile yet. So that's on our to-do list, is look to see if you've got any gravitational handles on these things, even with the shallower density profile. I don't know the answer to that yet. But yes, by looking at annihilation, you are probing inflation subject to the assumption that dark matter is a standard thermal relic.
Would there be another scenario which would give rise to those compact or densities in the universe, as opposed to, instead of some spike in inflation and potential, something like that?
On scales less than an Earth mass, yes. On scales greater than an Earth mass, no. And I'll say in a minute what sets that scale. But yes, on scales less than an Earth mass, yes, and that's what I'm about to talk about. Scales more than an Earth mass, no, it's really got to be inflationary. So this is the first second in the universe, but let's look at it in terms of temperature instead. We don't know when inflation happened or what energy it happened at. But let's say it happened at about, gut scale or just below, so 10 to the 15 GeV. That's usually our best guess. Big Bang nucleosynthesis needed to get started, get all the actors lined up in their right positions at about a temperature of an MeV. So we have 18 orders of magnitude in temperature evolution between inflation and Big Bang nucleosynthesis that we have no knowledge of. For comparison, the universe is only cooled by 10 orders of magnitude between BBN and today. So by my clock, this is most of the history of the universe. So what happened? What happened during this epoch in the universe? What happened during the gap? Well, the universe was once dominated by a scalar field, we think. Be that the inflaton or other scalar fields you may or may not have running around your high energy theory picture of the universe. String theory likes these things. An oscillating scalar field around the minimum of its potential behaves like matter. It effectively has zero pressure. It redshifts like matter. It clumps like matter. Think of it like matter. It's also possible that you could have actual other massive particles running around the early universe. Hidden sector particles and hidden sector models for dark matter generically predict these things. And the key is that the universe expanded so much during this time that even if you just started out with a little bit of massive particles, they would quickly come to dominate the universe before Big Bang nucleosynthesis. Now, eventually, the one thing we do know is the universe was radiation dominated at Big Bang nucleosynthesis. So we need to reheat the universe, get into radiation domination by a temperature of 3 MeV. Anything colder than that, we mess up Big Bang nucleosynthesis, and that's bad. So this is what sets the scale. How much dark matter was within the horizon at this time? Things smaller than that, you can mess with. Things bigger than that, you cannot. So what I'm postulating here, or what I'm hoping to explore, is consider this gap and put in an early matter-dominated era, be it an oscillating scalar field or a massive particle, and plop that in right there. What does that do? It has implications for dark matter production and for the early growth of structure. So I've alluded to already dark matter. Where did dark matter come from? WIMPs are a favorite dark matter particle. Why? Because they have a really nice production mechanism, affectionately known as the WIMP miracle. How do you do this? You start with a hot radiation bath with photons or leptons or even quarks, hot enough that they can pair produce my dark matter particle in particle-antiparticle pairs. The universe expands and my radiation bath cools. Eventually, pair production stops, but annihilations continue. Annihilations continue until the particles can't find each other anymore. Basically, the age of the universe becomes less than the time between collisions, and you're left with an ambient density of dark matter throughout the universe. That density matches the observed density if you have this cross-section on the order of 10 to the minus 26 centimeter cubed per second. So this is the cross-section I was assuming in the first part of the talk. This lines up nicely to what you might expect a weakly interacting particle with a mass of a few hundred GeV to have. Ah, maybe the dark matter is a weakly interacting massive particle. However, this has a major assumption. This assumes that the universe was radiation dominated at temperatures greater than 20 GeV. And we don't know that that was the case. Without that assumption, you are totally free to basically have any cross-section you want and get the right abundance out in the end. So from a miracle to mess, this is the amount of dark matter as a function of mass. The red line is the observed amount. And so the old WIMP miracle was the fact that some of the blue points, these are SUSY neutralino points, lied on the red line, and that was the miracle. But if you change the reheat temperature, then these points all start falling below the line. If you add in non-thermal production, they all go above the line, and basically we don't know anything about dark matter properties if we don't know what happened in the early universe.
So how do we read this part? What is each point?
So each point is a supersymmetric model. This is pre-LHC, so probably some of these have been ruled out by now. So each point is a model, and the red line is observations. And so this is basically the standard WIMP miracle, that there are some points that lie on the red line. But the key is that these models can predict more or less dark matter if you muddle around your knobs on what happened in the early universe.
What is F?
How much dark matter was created non-thermally. So how can we make progress? How can we hope to get at, was there an early matter-dominated era? Well, the other signature it would have would be on the growth of structure. So this is showing the amplitude of a density fluctuation as a function of scale factor A. It starts out constant, and then during an early matter-dominated era, gravity will allow it to grow linearly with scale factor. Once the universe becomes radiation-dominated, it switches over to logarithmic growth. So what this does is it means that small scale fluctuations, sub-Earth mass fluctuations, get a head start on growth. They can start growing early. And so they are enhanced. And this is a plot that shows that enhancement. Sigma m is the characteristic fluctuation of density in spheres containing mass m as a function of mass. And when you see here for the different reheat temperatures, that amount of fluctuation, that amount of inhomogeneity increases rapidly as you go to scales smaller than this reheat mass, which is the dark matter mass within the horizon at reheating, which is sub-Earth mass. And the fact that we know that reheating had to happen before BBN is what limits this to be sub-tens of Earth masses, microhalos. So we're going to look for these effects using the same technique we did before. We're looking for dark matter annihilation. And actually, I'm going to skip that and say, okay, how much of the dark matter is in these halos? So this is showing what fraction of the dark matter is in microhalos as a function of redshift for different values of the cutoff scale set by the dark matter microphysics, i.e. the smallest dark matter structures, compared to the reheat scale set by reheating. And what you can see is that in the standard scenario, with no early matter-dominated era, you have to basically wait until a redshift of about 50 before you start forming structure at all. Even at a redshift of 50, only about 4% of the dark matter is in halos. But 90% of the dark matter can be in halos if you have an early matter-dominated era. So now the basic building block of structure formation is no longer dark matter particles. It's actually little dark matter clumps. So everything's clumpy, and it's clumps all the way down. We've actually done some simulations of what these clumps look like. So this is what a clump would look like in the absence of an early matter-dominated era. This is like the first dark matter halo forming at a redshift of 30. And this is what it looks like with an early matter-dominated era. And you see it's just clumps within clumps within clumps within clumps. And so we can look for this in the dark matter annihilation rate. We can say that the dark matter and probability of a dark matter particle finding another dark matter particle and annihilating is much higher in this picture than in this picture. Now there's a caveat, there's a catch. These same scenarios make the cross-section needed to make the dark matter smaller. So you have a smaller cross-section, but you have a higher collision probability because you've got higher density. And these two effects conspire to basically put you right where Fermi can observe. So we've done these simulations of forming the halos. Indeed, with an early matter-dominated era, you get halos forming very, very early, these little microhalos. And the microhalos clump into larger halos, and so you've got basically halos within halos. As opposed to without an early matter-dominated era, you don't get anything until much, much later in the simulation, and then it's a smooth object. So, you form these halos, they then fall into galaxies. And so then we've done simulations of how these halos respond to falling into a galaxy and being tidally disrupted while they orbit their galaxy. And we find that they do get disrupted, but their inner region stays pretty close, pretty intact. This is a plot of the annihilation rate within the halo as a function of its initial annihilation rate for different orbits and different eccentricities. And so we have developed a model for this evolution of the annihilation rate and used it to predict what is the actual signal from a microhalo within a dwarf spheroidal galaxy, specifically Draco. So we looked at Draco, and we modeled how much each halo, each microhalo, would be stripped at a given location in Draco, and used that to build a prediction for what the annihilation signal from Draco would look like. So this is the black is the unsuppressed signal from the microhalos. It just tracks the density profile of Draco. This is degrees from the center. And then as you change the EMDE parameters, you end up with more or less suppression based on how many of the halos are being destroyed in the center region. And we can use these to actually set constraints. So for this specific model, this reheat temperature, we can actually rule out the thermal relic cross-sections that would give you the right density based on observations of Draco. And so right now we've just done this like one parameter set. So the full parameter scan is in progress. But it is possible. We can constrain these scenarios. And in particular, this can rule out some Beano matter, dark matter particles that were otherwise viable. Now there are some scales of uncertainty, so there is some more work in progress, and I'm going to skip talking about the details of that and just summarize and say, so we can use these Earth mass microhalos to probe this gap between inflation and the onset of radiation domination. Gamma ray observations right now are already strong enough to really start chomping out sections of this parameter space for thermorelic dark matter during an early matter-dominated era. And this is simultaneously telling us both something about dark matter, where it is and where it came from, and it's also telling us about how the universe evolved in the first second. I think that's really exciting. Thank you.
Is there a mass, is it the lowest mass microhalos that dominate this constraint, or is it?
Yes, and that's why this constraint is so sensitive to the dark matter microphysics that determines the scale of those smallest halos. So that's an area that we're actively working on. It's always the smallest halos that dominate because they're the first that form. And the first that form are the densest. And so it's the densest nuggets that form, dominate the annihilation signal. And so the scale of what exactly is the smallest halos that form, that's set by the temperature of the dark matter particle, its interactions with normal matter. All of these physics have not been studied in an early matter-dominated era before, so a lot of our investment has been going into trying to pin down how dark matter decouples in an early matter-dominated era. How does it free stream in an early matter-dominated era? What sets that cutoff scale? Because that cutoff scale really does also affect the constraints.
So if this is true, then you're saying most of the stuff is in these clumps.
Mm-hmm.
What fraction of it?
That is mainly, so initially 90%, all of it. Then some of it gets stripped. So with a picture that you would have of this universe would be at a redshift of like 200, all of the dark matter is in these clumps. But then as larger structures form, these microhalos start to get stripped. And judging from our simulations of the stripping, they lose about 60% of their mass in the process of their stripping. So you would expect something like the Milky Way, say, to be about 60% of the dark matter in the smooth component of stripped wreckage of microhalos, and 40% in the still core nuggets of the microhalos. But those core nuggets would still dominate the annihilation rate.
But if you have one of these, ton of xenon waiting for dark matter to run into you,
yeah,
that would just change you by an order 1.
It would change it. It would actually it would change it by. It kind of depends on, because that 60% is averaged over the whole galaxy. It's of course higher in the inner region. That's where most of the stripping occurs. In our local neighborhood, we're so far out. There's actually not much stripping in our neighborhood. So for our neighborhood, this story is doubly bad for the direct detection folks, because one, the type of particles I mentioned, Beanos, that give the right relic abundance in these models are already extremely weakly interacting and are difficult to see. And then at least in our local neighborhood, we would expect the dark matter to be extremely clumpy. And the chances of us being inside a clump are kind of low. So this is just universally bad news for the direct detection efforts.
So I mean, you focus on seeing the light of dark matter, but I mean, there was a discussion of annihilation cross sections, and so it's different. So I'm wondering if you can somehow use another way to disprove your hypothesis or prove your hypothesis. I mean, essentially, when you have lots of these mini-halos with high enough mass, shouldn't you see a blurry universe? Shouldn't you see the CMB power spectrum differently than if you don't have that in the middle?
The scales
That
are
doesn't work.
so different. So these microhalo scales are way, way, way smaller than anything we could resolve in the CMB. Way, way smaller than anything that's even affected by the lensing of the CMB. In terms of actually forming a galaxy, remember that everything we know about halo formation and nonlinear structure growth, we've mainly learned from cosmological simulations. And these cosmological simulations typically use particles that have mass of 1,000 solar masses. And you form a galaxy just fine using particles with 1,000 solar masses. So in terms of the dynamics of our observed universe, it really doesn't matter whether the dark matter is in a bunch of Earth mass clumps or not. The hierarchy of scales is that profound.
Is there any other way to test your hypothesis other than saying
The
you need to have
annihilation?
radiation?
So the first part, the solar mass mini-halos from inflation, those can give gravitational signatures. So like I said, analyses have been done with the old profile. We just discovered the new profile 6 months ago, so we haven't gotten around to refining those for the new profile. But at least with the old profile, Gaia was going to say something interesting about them through astrometric microlensing. Pulsar timing arrays, where we had a lot of constraining power. We don't know yet how the new model affects those constraints. But the hope would be that those could have some gravitational handle on them that would make it independent of the dark matter particle. For the Earth mass, it's pretty hopeless. The Earth mass microhalos, there's just no lensing signature that you're ever going to see from a diffuse Earth mass microhalo.
So if you form nonlinear structures in this early matter phase, does that affect the photon perturbations at all?
So generally speaking, I'm not forming the structures during the early matter dominated phase. I'm forming them after the early matter dominated phase. They just get a head start. So basically, your typical density fluctuation is on the order of 10 to the minus 5 initially. What we're usually looking at is that it grew from 10 to the minus 5 to 10 to the minus 3 during the early matter dominated era. This means that it actually goes nonlinear at a redshift of 500 instead of redshift of 50. So it's still forming the halo in standard matter domination. It's just forming it earlier. It gets a head start. Forming structure during the early matter dominated era itself is actually problematic. That's bad for the signals. And the reason why that's bad for the signals is the structures that then form during the early matter dominated era are mainly bound structures of whatever was dominant, this oscillating scalar field or the massive particle, whatever was dominating the universe during that time, with only trace amounts of dark matter in it. Then most of the mass inside that halo turns into radiation and evaporates. The dark matter that was in it isn't bound anymore. And so any structures, any nonlinear structures that formed during the early matter dominated era actually only serve to heat the dark matter. And they wouldn't have any observational signal. So the key thing, what gives you the observational signal is things that grew during the early matter dominated era, but then didn't actually collapse until after that.
Has anyone studied dynamical friction or just gravitational scattering of dense mini-halos? Let's say if you have mini-halos of 100 solar masses, then a dwarf galaxy would be essentially made up of, let's say, 10 to the 5 dense clumps.
Exactly.
Right? And there could be gravitational interactions.
Yeah, I don't know. Not that I'm aware of.
I feel like that stuff's been done with much larger cases, like making the galaxy out of 10 to the 6 solar mass.
Right, and then you do get into some dynamical friction. You get into some sine noise issues when you've got from just a structural information point of view, I know 10 to the 4 solar mass primordial black holes.
Right, that's
are kind of the upper bound. Therefore, you start really seeing the manifestations of discrete dark matter. So if you're saying, could you imagine it being effective, it would actually just hundreds of solar masses.
Yeah, so maybe that.
I don't, my guess would be no, but I haven't done the calculation.
If there are no more questions, let's thank Adrienne again.